How can you think that we can understand reality because we are so far away? We are nothing but everything. We have so much data with reality, so we cannot understand, or we cannot pretend to see. Sorry. No, we can discuss next week, or
all right, so we will. I have the same. Okay, so we'll start slowly. So just a typo that for some reason for the whole of lecture on Tuesday I forgot one index. So of course that states that are of the that are on a composed Hilbert space. They can have a different index in the first system and in the second system. And one example was like this state. This. Okay, and for the whole lecture, I forgot to have the second index here. Okay, so thanks to the student who pointed this out. Today, we will now leave the entangled states and product spaces apart for a while, and we'll continue talking about uniform dynamics. In particular, we'll look at a very simple case called uniform dynamics, and I'll explain what this is, but it will be when the Hamiltonian does not depend on time, essentially. Okay, so up to now, what have we done? So we looked at, so far, the story is, we have states which are some vectors in spaces or positions, vectors in several spaces. We know that reversible dynamics, we've not talked about irreversible dynamics yet, and it will be a while, but reversible dynamics, we saw them as saying, for example, that state time t by some unitary matrix, kind of the initial state and the initial time and the final time, multiplied by the initial state. Okay, so we saw this, and the other thing we saw was Schrödinger's equation, which is when we care about evolutions in this parameter t. I mean, we don't care just about applying a gate, like we saw, like the NOT gate or the bit flip, the phase flip, the Hadamard, and so on. We want to see really how this state evolves slowly in time. And what we got was this equation. And we saw a way to derive it just from here, right? Starting just this. And last week, we derived it. This where this thing is the important property is that this matrix H is Hermitian, meaning that H equals Hermitian. I'll put the lecture notes, by the way, later this week online, and this we call the Hamiltonian. And this thing here is a constant. It's called the reduced Planck constant. And just to give you an idea of what it is, it's about 10 to minus 34. Yeah, that's the right reaction. So some units, it's units to kind of transform. This is going to be units of energy. So this should be energy times time because you have here a time derivative. What's important that is very small, okay? And essentially, you're going to see later that when you have a quantum particle moving, if the mass of the particle is very small, for example, in case of an electron, yeah, I'll be there in a second, then we see quantum effects very obviously, but as this mass gets bigger, because this constant is so small, you don't see the effect. It behaves like a classical particle, right? This is one of the ways of recovering the classical limit, is by saying, well, if my system of interest is very large compared to this constant here, then you don't see so much of the quantum effects. Yes, there was a question here.
Can you explain the reversal dynamics equation again? I'm having a hard time understanding T0 and T and why that's.
Okay, so yeah, I'll answer that, and then I'll answer a question that was asked last time. So this is just saying like, oh, how do I get a new state? From the original state is just by applying a unitary. Okay, and now I just parameterize these things by saying, well, this is the initial state, saying the state at T0. This is going to be the final state, the state at 10T. So this unitary could be anything. We'll see now a special case, but you know, you can characterize it by, it should depend at least in the initial state and the final state.
So the reversal dynamics part is that you use the unitary.
The reversible dynamics part is that I use the unitary, so I can get this back by applying. Right?
Yes.
So there's a way to to recover the initial state from the final state by right? Okay. So very good question that I was asked last time is, how did people get up to this equation? Like, did they also start here and then do just this derivation? And the answer is, I don't think so. Look, physicists were building quantum mechanics given their whole background in classical mechanics. In classical mechanics, I don't know if you learned maybe Newton's laws, but there's another way to formulate things in terms of conservation laws, of finding all the classical dynamics. There's like the Lagrangian, but also the Hamiltonian, which, you know, in some limit behaves more or less like this, in some limit. So they were already, I mean, they knew that some operator that expresses energy should be determinate for the dynamics of the system, right? So today, I mean, the difference between this class and the quantum computing class is that we're going to look at how physical systems actually behave. So we want to, you know, you want to apply this to actual systems we can see in the lab and then in life. And to do this, because, you know, in general, this is a differential equation and you can solve analytically up to the hydrogen atom, and anything more complicated than this, you need to simulate numerically, essentially. So we're going to look at the simplest case, and that's going to be called uniform dynamics. And like I said before, that's going to be when the Hamiltonian does not depend on time, but we don't start from there. We start by saying that we simply demand that this unitary that depends on the initial time and the final time, or I use there T1 and T0, it actually only depends on the interval of time. So it doesn't matter if you started at second 10 or at second 20 or second 30, it only matters that it runs for 5 seconds, for example. Okay. So what are some immediate consequences of this? Is that, well, if you have the unitary that depends on this, so let's call this interval delta t. So u of delta t, u of delta s, this is going to be delta t. I mean, look, one example of this is like I put my cup of coffee in the fridge for 5 minutes. What happens to it? I don't need to know if I did it at 7 in the morning or at 11 in the morning or at 3 in the morning. It doesn't depend on the initial time, just on the total time that it was in the system, the fridge. So we have this. right? Is this obvious why? Because it's like U of T2 and T0, and here is U of, let's say, T1, T0, and here is U of T2, T1. And now you replace each of this with this, right? So then you get minus, minus, minus. Okay. So that's, I left my note. Charging. Okay. So if I take this and now I say, well, if in particular, if delta t is the same as delta s, and I swear I'm going somewhere with this, then I just put here the same time interval, so I get this unitary times itself, so I get u of delta t squared. This is u of delta t plus delta t, that's 2 delta t, right? And if I do it again, then I get cube here and I get 3 delta t. So in general, I get u of delta t to some power, I'm gonna need power L, I think. Will of u of L. Delta t. We're gonna use this because what we want to do is to find more about this, unitary and find more about the Hamiltonian for this special case. So remember that we had worked out. So first, okay, I'm just writing this unitary in its diagonal basis. Okay. It's unitary, so it has a diagonal, so it has diagonal basis, that's k. And these are the coefficients. And we found out a week ago that these coefficients are all normalized. So they're all written on this form E, I, and G is some function alpha k. Now this function is unknown. But now we just use this property here to find out more about this function. So let's call it 1. This 2. By inserting 1 into the other. Yes, is this a question? No. Yeah.
So where is the T2 coming from?
Oh, I just think of. Yes, look, T0, T1, T2, and this time we call delta S, and this time we call delta T, for example. Yeah.
T1, T0 equals T2 minus T1. Shouldn't it be T1 minus T0? Or maybe
So this T2 comes from my previous notation in the lecture notes. Sorry. There you go. All right. Okay. Were you holding your hand since I wrote this like 10 minutes ago? You can just say I have a question because I don't always see. Yeah. Because so what we found out last Thursday was that these coefficients all add norm 1, right? So you can, I mean, this is a complex number, so you can write a complex number as r times the I alpha, and what we found out is that this r is 1, so you only left this alpha. This alpha can depend on this delta t in a way that we don't know yet. So it's and depends on k because it depends on the eigenstate. There was another question. Sorry, I cannot hear you. It's a function. It's a function for now. So it's a function that depends on delta t. And we're going to try to find out more about this function. Okay. You can call it f if that's easier. Okay. All right. So now we want that u of delta t to the L, this whole thing to the L, we want this to be u of L delta t, right? That's this one thing here. And what does this look like? And I know that you already talked a little bit about this in the tutorial. Later on, I'll make a more general rule. But this means, so u to the L, if you take u in its diagonal form like this, then it's just, you just exponentiate all the eigenvalues. Okay, so in its diagonal form. Or in other words, so this is what? Sum over k. I'm just going to write this matrix in other words. So that, and now it would be here the UKs to the L, right? That's exactly what's there. But now we already know that the UKs are of this form. So I'll just write here e to the I alpha k, which is a function that depends on t, all of this to the L. Should be this. So e to the I alpha k. And now here where there's the delta t, we put L delta t. In other words, e to the I. So this exponent just goes inside here. L alpha k of delta t. E to the I, okay, of L delta t. So now, I mean, what's the function such that the function of L times the argument equals L times the function? In other words, so we have that L times this function of delta t equals this function of delta t times L, right? So for it to satisfy this property, it means it's a linear function. It means that alpha is just delta t times some constant, right? So this means that alpha k of delta t is just some constant times delta t. This is a constant that, and because this constant could be positive or negative, and because we know how everything's going to work out at the end, we just put a minus sign here. Okay, doesn't change anything because this could be anything. It's just a convention. To work out with some things later, I will show. Okay, is this clear? Yeah. Yeah.
The properties that we fix for the uniform dynamics, it's not a general.
Yeah, no, it's not general. No, it's not general, right? I mean, to go back to this example, if I just turned on the fridge in the morning, then it matches at what time I put the cup of tea or my cup of coffee inside there. Yeah. No, it absolutely matters, right? Because it tells you that it really tells that evolving 5 seconds here or evolving 5 seconds there, it's the same thing, right? So yeah, this will apply for systems like, I don't know, I have a magnetic field that's always the same, or I have some potential that I create in the lab that is always the same, that's not going to change. Yep.
You, the argument delta c to the power of L, right? So if when we take something like x to the power of L, do we just apply the power of L to the u, or do we also, you know, use consider a problem because
Okay.
imagine here sine x to the power of t. It's like sine. It's not the same thing.
So I will do this mathematical aside now then. I wanted to do it later, but I can do it now. It doesn't change much. Yes, so I'll about how we roughly do things in the discrete case for well-behaved matrices. And the continuous case is a bit more subtle, but in the examples that we'll see, it's more or less the same. Okay. So if you are in the future watching this and following the lecture notes, this is page 5. Page 5. So it's, I say mathematical, but it's sometimes it might mean more of a convention aside. So again, it's about how we evaluate functions on a matrix. Okay, so if you take A to be a normal matrix, meaning it commutes with a dagger. So this is a superset of right. So in particular, this applies to all unitary matrices. Then there exists a matrix D that is diagonal. And there exists a V that is unitary matrix such that A equals V, V tech, and D is this is just the eigenbasis of this matrix. So in particular, Hermitian matrices are also normal matrices. So when we talk about the complex function evaluated on a matrix, right? So if you have f of x is a complex number, and the argument is also usually a complex number, then if what we talk about when we talk about f of a, this is we diagonalize the matrix, and we just apply this to all the eigenvalues. So in particular, if you just write A in its eigenbasis, so if A is some sum over K of okay, then f of A sum over K of f of AK. Okay, right. So that's what we did there. Right. So I don't know if this was the question, but
My question is, so the delta t is not, that should not expect.
I mean, of course, this depends on delta t, right? So sorry, again, what's the question?
So it's not a function already, but in the, so U delta T is also matrix, but it's dependent on delta T.
Yeah.
It's not a function, yes. It's two different things. Like
I mean,
function and
so this is a matrix, which is a function of the delta T, right? But it's a matrix, right? I mean, if you want to be, it's an endomorphism on the Hilbert space. So it's a map from the Hilbert space to itself. Okay. In particular, if you write it in the diagonal form, the thing that depends on delta T are not the eigenvectors, but just the eigenvalues.
so is this a matrix consisting of functions?
So it's a matrix where every entry depends on delta T. Every entry depends on delta T. So you can see it as a function of delta T, of a complex function from C to from R to C. Okay. All right. So we go back to. So we already narrowed it down a bit. Right, so we're trying to find out more about this matrix and about the coefficients there. So what we have so far is that U of delta T is the sum over K of E minus I WK times delta T. Okay, and now these WKs are just numbers, are just complex numbers. Okay. Now, to find more about these coefficients, we're going to look at how it applies to specific special states. Okay. So you're going to see that, well, the Schrödinger equation should apply to all states, and you're going to look in particular how it applies to these states here. Okay. So, and just to simplify a bit the notation, let's say without loss of generality, we just say, well, let's say call this T00 so that we can just call delta T. Okay, so that we just don't write delta all the time. And now we take special case. We take this initial state to be one of the eigenstates of the Hamiltonian. Yeah. And we see how it acts here. Well, what happens when you act? Sorry. So at time t, what happens when you act with a matrix on one of its eigenstates? You get the eigenvalue corresponding to this, right? So you can make the whole calculation in direct notation. It's very nice. But think that it's just the, I mean, it's just, this is an eigenstate of this matrix, so you get the eigenvalue out. Okay. Okay, and now we're gonna go and we will plug this whole thing in the Schrödinger equation. So far, are we okay? This case is, by the way, the states are called stationary states because, I mean, if you look at it, when you evolve them, they don't really change. They just get this global phase. And as you saw, the global phase does not change the outcome of measurements. So if you're looking at only the subsystem, then you can think of them as not changing. Okay. All right. Yeah.
So what is the I know what the goal is.
Yeah.
But what is the phase of the system? Just like what is the phase? What do you mean?
So the phase is like this complex number that of module 1 that appears in front of the state. Yes.
There's probably more to it.
There's more to it. I mean, to see how it affects things, and you need to look at. I mean, you saw that it doesn't affect the outcome of local measurements, but it will affect the outcome of global measurements. We can look at some examples maybe next time then. Yeah. All right, so let's just plug this in on the Schrödinger equation and let's see what happens. So what was it again? It was h psi of t equals I h bar dt. Okay, and now we just replace this state with that state we saw there. So what was it? E to minus I wkt. Okay. I h bar dt. E to minus I wkt. Okay. So now we can do this derivative. So let's do the right-hand side first. So k does not depend on time, right? It was just the eigenbasis of the unitary. There's no time here. So k is going to stay. And now we just need to take the derivative of an exponential, which gives us minus I wk times. Okay. That's just the derivative of this thing in order to t. On this side, I mean, nothing happens. This is just a number again. This whole thing is just a number. So we can put this part here and take the number outside. And this number is the same as that, so they cancel out. So then we end up with what? And I times minus I is 1. So then we end up with h k equals h bar wk. And what does this tell us? Tells us a lot. First, it means that the eigenstates of the unitary are also the eigenstates of the Hamiltonian, right? With this eigenvalue. And it tells us that, so I told you before that this represents energy, and that's kind of by definition. We can look into this later. But then this means that these are the eigenvalues of energy. So you can call it EK. And these are eigenstates. And this is what we call the time-independent Schrödinger equation. It's just this. H k equals EK. Okay. So it also means that we can write this matrix H as this is 0, 1, and so on in basis. Okay. And essentially, we'll see later that in order to know how any state evolves in a system that is characterized by a Hamiltonian, all we need to know is this matrix H, which means we need to know all these coefficients, and we need to know all the stationary states. And so let's do just one more thing before we go, which is to express now the unitary in terms of H, right? They seem to be very related. They share the same eigenbasis. We saw that their eigenvalues are kind of related. So let's just try to express the evolution in terms of H. U of t of H. And the way to do it is again to plug it in the Schrödinger equation, but now we do it for any state. So this was a special thing for the stationary states, for this eigenstate, to find out what the eigenvalues of H were. And now we do it for any state. So we have H t equals IH bar. That's H. We just replace this here with U of t by 0 equals I H bar ddt of U of t 0. Now note that this phi of 0 also does not depend on time, right? This is just initial state, does not depend on time. So we can put some brackets here. And this equation should be true for all initial states. So, I mean, in particular, we can choose all the initial states that end up forming a basis of this space. And, you know, if this matrix times this state must be the same as this matrix times this state for all initial state, for all states, then it means that the two matrices must be the same. Right, so from here we take that H U of t equals IH bar ddt. So let's just take all the constants to this side. Okay, so I'll do it here. What we get, minus I of H bar, H U of t equals ddt. Now, we don't need to know a lot of differential equations for this course, but look, this is a constant, right? It's a constant matrix, but it's a constant. It does not depend on time. So what kind of thing, when derived, gives itself times a constant? It's going to be the exponential, like we saw before. Right? I mean, if you remember one differential equation is probably this. Yeah. Yes, two questions. Yes, on the back first.
Yeah. No.
Oh, please just say you have a question. I can't always hear. Yeah. Yeah. So
the WK delta T, right? Much is that the constant. So we went from the eigenvalues to the representation using the exponential, right? Like how is the WK delta T? Like what's the y delta?
So we went in the thing that I already raised. Yeah, I raised, right? I raised it, but we saw that the unitary could be written in these terms because before there was a function here and we found out, well, this function must be linear, right? Therefore, it was just a WK times T. And now we saw at the end of the day that this WK depends on, I mean, that this WK is an eigenvalue of the Hamiltonian if you multiply it by this H bar. Were there questions at the end? Yes?
I want to ask how do I always got the minus from I directly?
Yeah, because I put it here, and then 1 over I equals minus I.
Okay, that's
Yeah, that's what happened. Yeah. Yeah. Okay, so then the conclusion, and you can see that it works, and we will not derive it, is that then the unitary for time t when the Hamiltonian is constant. So for this uniform dynamics is given by this. Yeah. If the Hamiltonian changes with time, then this changes a little bit. But you can see that the dt of u of t is the dt of this thing, which is minus I h bar h. And then the same thing again. But this is just u of t. And that's this equation that we wanted to satisfy, right? So this is really kind of the big conclusion. It's that you can express for uniform dynamics, so when the Hamiltonian does not depend on time, so our evolution does not depend on the initial time, just on the total duration, then you can always express the unitary as the exponential of the Hamiltonian times t and a constant. Then I'll just write 2 more things before I let you go. So what does this mean in Dirac notation for the form of the Hamiltonian and the unitary? So if you have your H, we said sum over K of those eigenvalues times K, then U of T sum over K e to minus I e K over H bar. Because of the same thing, right? The exponential of a matrix, you take the diagonal form and you do the exponential of the eigenvalues. Okay. And we saw that we can write this a bit simpler with this WK, which is EK. Or if you want. Okay. For continuous systems, it's going to be very similar. So we'll see this later on. The only last thing we're going to say is that if you have a very small interval of time, okay, so t small, then we can approximate this exponential with a Taylor expansion. Okay, so then u of t, which is e to minus e. This is going to be approximately the Taylor expansion of an exponential, which you saw. We do the identity minus I t over h bar plus some other terms that only depend on t squared or smaller. Okay. So for very small times, we can do this approximation. This is used a lot for example, in quantum computing for Hamiltonian simulation, when you want to simulate a large Hamiltonian via a small quantum circuit, then you use a bunch of these techniques to do it. But you'll see this in QIP, I think. Okay, we leave this here, and then Yeah, we'll continue next time and we'll see examples. Yes, I'll see you next week. Hey, we survived.